In this video, we discuss about modeling enzyme kinetics. We will focus especially on the very famous Michaelis-Menten kinetics. Enzymes play a catalytic role in biology. They are highly specific and they remain unchanged by the reaction. One enzyme molecule catalyzes about 1,000 reactions per second, and the rate acceleration is about 10 to 6 to even 10 to power 12 fold compared to uncatalyzed spontaneous reactions. Enzymatic reactions usually involve several steps and are described using more complicated models than mass action. We will discuss in the following the model of enzymatic reactions using Michaelis-Menten. In 1902, Brown proposed the following reaction model for irreversible enzymatic reaction. An enzyme and a substrate react in a reversible way to form a complex where the enzyme is bound to the substrate, and then as a result of this, we are going to get the enzyme and a product of that reaction. Now, obviously, if we write a mass action based ordinary differential equation model, we will write one equation for each one of the four variables of this model with the result shown on this screen. In 1913, Michaelis and Menten assumed that the first part of the reaction is much faster than the second one. And this can be true if both of these kinetic rate constants are larger, or in fact much larger, than the kinetic rate constant of the second reaction. In 1925, Briggs and Haldane also showed that in some conditions it may be assumed that the complex where the enzyme is bound to the substrate reaches quickly a steady state. This is the case, for example, if the enzyme is saturated by the substrate, or in other words, we have much more substrate than we have enzymes. In any case, both assumptions lead to assuming that the differential of this complex where the enzyme is bound to S is zero. So in other words, E bound to S is a constant. So let's investigate what consequences this assumption has. So if we start from the mass action based ordinary differential equation model consisting of these four reactions, we will notice that E plus E bound to S is obviously a constant in the model because we only have so many enzymes and we don't lose enzymes, we don't gain enzymes in this model. It's just that it switches from being free to being bound to S. So let's denote by E total the sum of E plus E bound to S. So that means that E is E total minus E bound to S. Now, if the differential of E bound to S is 0, in other words, if E bound to S is constant, then equation 2 becomes simply K1 ES minus K minus 1 plus K2 times E bound to S equals to 0. Then 2' can be rewritten based on 5. And when we replace E with the expression E total minus E bound to S, we are going to get this equation. So from this equation we can obtain the expression for E bound to S, and that's written in this equation that I show on the screen. So based on 2', we can now rewrite equation 1, and that will become ds to dt equals minus K2 times E bound to S. If we define now Vmax to be K2 times E total and Km to be this K minus 1 plus K2 divided by K1, then we will obtain that ds to dt equals minus Vmax times S divided by S plus Km. And dp to dt equals Vmax times S over S plus Km. So, as an intuition, Vmax is the maximal rate, or velocity if you like, that can be obtained when the enzyme is completely saturated with a substrate. and Vmax is in fact K2 times E total, just like we defined it. Km is the Michaelis constant. Km equals K minus 1 plus K2 over K1, and it's equal to the substrate concentration that yields the half maximal reaction rate. Here is a plot of how the rate of a Michaelis-Menten reaction depends on the substrate concentration. For low substrate concentration S, the reaction rate increases almost linearly with S. For high substrate concentration S, the reaction rate is almost independent of S. Vmax is the maximal reaction rate that can be achieved for large substrate concentration, and the Michaelis-Menten constant is the substrate concentration that gives exactly half of Vmax.